Hello everyone. Our section today, Calculus 2. This section is introduced in the period of coronavirus spread. God save you and save our dear country. Chapter 3, Definite Integral. If we have a function f of x which is continuous function defined on the interval from a to b, closed interval from a to b. That curve represents the function. So we can find the tangent at any point. For any point we can find the tangent. Tangent is equivalent to the definition of the first derivative df by gx. So we can say that df by gx exists for the same interval from a to b. Now this function is integrable. By the converse definition between differentiation and integration, we can say also that f of x is also integrable. Integrable, but not integrable at all in the same interval, that's closed interval from a to b. Now we can write the definite integral in the form integration from a to b f of x dx, called definite integral. F of x is integrand, that's the function. It's possible to find the integration. Is integrable, it's also integrable. And a and b called limits of integration. So a is lower limit and b is upper limit. Now we also know that definite integral gives area under the curve. Definite integral gives area under the curve bounded from point A to point B, as you see. So definite integral must be value, not variables. Not variable. So definite integral gives a number. Doesn't depend on x. So if we find definite integral and the value was function in x, there is a mistake. Theorem 1. If f of x is continuous function on the interval, closed interval a and b, then we can say that definite integral gives f of x plus constant. But definite integral gives us value, not variable. Doesn't depend on x. So we can write it in the form f of x as f capital of x is the result of integration of f of x. And a and b is limits of integration. We can substitute by b upper limit, difference substitution by a lower limit. That means that first we have two steps to find definite integral. First, we define the integral directly. Step 2, we represent x first time by b upper limit and second time by a lower limit, and the sign between that is negative. Some properties of definite integral. First, definite integral from a to b dx equal, we have two steps. First, we should find the integration. Integration for dx is x by the same limits from a to b. Using substitution, upper limit minus lower limit, put x by b, it's equal b, and also put x by a, that's equal a, it's equal also at all b minus a. So number 2, if we have the integration from a to a, that means that the function and integration has the same limits. From 1, if a equal b, that means that the integration gives 0. The integration gives 0. So at all we say that if the bounded of integration equal, that means the integration equal 0. For example, integration from 2 to 4 and 2 for sine x dx equal 0, and from 1 to 1 for this function x plus 7 all power 100 also equal 0. Assume that a and b are equal, that means value will equal 0. 3. If we have constant k in the integration, we can point constant k outside the integration and put the integration, do the integration, find the value of integration, and substitution with limits, upper and lower limits directly. If we have two functions, sum or difference between two functions, then we can write it as definite integral for the first function, positive or negative, definite integral from a to b for the second function. 5. If we have point c between the interval a and b, if we have point c between the interval from a to b, that now we can divide the area, the total area, into two parts, first part and second part. That means that the area of the first part plus the area of the second part give us the total area. Now the integration from a to b, we can write it in the form integration from a to c plus integration from c to b. Number 6. If we have odd function, so limits of integration not equal, but the same with different sign. Negative a and a, negative 2 and 2, negative 1 and 1 for the same function. If this function f of x is odd, also the result will equal 0, directly equal 0. For example, integration from negative 1 to 1 for x cubed, we notice that x cubed is odd function, as the power is odd, then the function depend on x is also odd, so the result will equal 0. And for sine x is odd function, and also tan x is odd function, but cosine x is even function. From negative pi over 2 to pi over 2, that means that the result will equal 0, depend on 6 properties. Number 7. If f of x is even function, also from negative a to a, negative 2 for 2, and negative 1, negative 3, negative pi over 2 and pi over 2, but the function in this case is even. So we can write it in the form 2 integration from 0 to a. For example, find the value of integration from negative 1 to 1 for x squared gx. X squared is even function, so we can write it in the form 2 integration from 0 to 1 for x squared. To find definite integral, we have two steps. First, we find the integration directly. Second, we using substitution by the lower limit and upper limit. X squared integration is x cubed over 3 from 0 to 1. That means that it's equal, put x by 1 over 3, put x by 0 equal 0. 1 over 3 times that's equal to 2. That's meaning that we have 2 over 3. Without using this property, direct integration for x squared is x cubed over 3 from negative 1 to 1. Put 1 over 3, and putting negative 1 over 3, negative times negative equal positive, 1 over 3 plus 1 over 3 equal 2 over 3. The two results are equal. Let we have some examples on definite integral. First example, evaluate the following integrals. Integration for x cubed dx from negative 1 to 3. Notice that the limits not equal and not equal by the opposite sign. Now we using the two steps. First, we find integration directly. Second, we substitute by the upper and lower limits. Integration for x cubed is x power 4 over 4 from negative 1 to 3. Let we put 1 over 4 outside. That means that we have x power 4 bounded by negative 1 and 3. Put x by 3, that's equal 3 power 4, and x by negative 1 power 4, negative 1 power 4 equal 1, 3 power 4 equal 81. That means that it's equal 80 divided by 4, it's equal 20. Example number 2. Definite integral from 0 to pi over 4 sine theta d theta. We have two steps. First, integration for sine is negative cosine. Negative cosine from 0 to pi over 4. We put negative outside. Cosine theta from 0 to pi over 4. That means that cosine pi over 4 minus cosine 0. Cosine 0 equal 1. Cosine pi over 4, 1 over root 2 divided by negative sign. That's equal 1 minus 1 over root 2. Example 3. Definite integral from 0 to 3 for the modulus function x minus 2 gx. Any function given by modulus x minus 2 or any type of function between the modulus, so we should use definition. That means that x minus 2 in opposite form x minus 2 and in negative form 2 minus x. Put x minus 2 equal 0. That means that x equal 2. We can write the definition also. X more than or equal to and x less than 2. In this integral, we notice that x is defined in the closed interval from 0 to 3. We have bounded by 2. So, from 0 to 3, we put point 2. We have two regions. 0 from 0 to 2 and from 2 to 3. We notice that region from 0 to 2, that means that x less than 0 depend on function 2 minus 3. That means that the first part will have the limits from 0 to 2 and function 2 minus x. And second part from 2 to 3, it's x more than 2 with the function x minus 2. So we use limits from 2 to 3 for the function x minus 2. We adding the first integration and the second integration. We have the total bounded integration from 0 to 3. To find this integration from 0 to 2, give it to x. x squared over 2, and also x squared over 2, and 2x, but different limits. Firstly, we substitute by 2. It's equal 4 minus 4 over 2. By 0, it's equal 0. Second part, by 3, 9 over 2, negative 6, by 2, 4 over 2 minus 4. It's easy to find this value. It's also will equal 5 over 2. Note, we notice that d by dx for sine minus 1x, it's equal 1 over root 1 minus x squared, and also d by dx tan inverse x equal 1 over 1 plus x squared. Remember case, if we have a function beside another function, if the first is the derivative of the second, then we adding 1 to its power and dividing by the new power. Let we see the following example. Example 4. Definite integral from 0 to 1 over root 2 for sine minus 1x over root 1 minus x squared dx. Now, we notice that root 1 minus x squared has a relation with sine minus 1x. It's a derivative. 1 of this root, 1 over this root is the derivative of sine minus 1x. So we write it in the following form. Now, d by dx for sine minus 1x is 1 over square root 1 minus x squared. That means that the function beside sine minus 1x is its derivative. So we adding 1 to its power and divided by the new power. Its power is 1. Its power is 1. So we adding 1, then power 2 over 2 from 0 to 1 over root 2. Substitute by 1 over root 2. That means that sine minus 1 over root 2 squared over 2 by 0 sine minus 1 0 all squared over 2. That's equal 0. Sine inverse 1 over root 2 equal 45 by over 4 squared. That's mean by squared over 16 over 2. That's give us by squared over 32. Another example in the same point. Definite integral from 0 to 1 e power tan inverse x over 1 plus x squared dx. We notice that there exists a relation between tan inverse and 1 over 1 plus x squared. That means that the derivative for tan minus 1x is 1 over 1 plus root x squared. We put it in the following form. 1 over 1 plus x squared times e power tan inverse x dx. From chapter 1, we said that for exponential function, if the derivative of the power of the exponential function beside it, that the result will equal the same exponential function. So the value of this integration is the same exponential function e power tan inverse x for the same limits 0 and 1. 1, that means that e power tan inverse 1. 0, that means e power tan inverse 0. Tan inverse 0 is 0. E power 0. Tan inverse 1 is 45 by over 4. So the result will be e power by over 4 minus 1. The following example show that integration, definite integral from 0 to pi squared cosine root x dx equal -4. Notice that we have type of integration, method of integration, what is called substitution. Case 1 is algebraic substitution. Depends that we can cancel the root. We put root x or any root by y and find the value of the integration and return this step to find the value of the integration by x. But definite integral gives value. That means that if we put root x by y, we'll have the same value. Now, using substitution, algebraic substitution, that we can put root x by y. Root x by y. Left hand side is the definite integral from 0 to pi squared cosine root x dx. We put root x by y by squaring x equal y squared. Now we should find also dx. So dx equal 2y dy. But in chapter 2 we haven't bounded integration in this form. But now we have two bounded or two limits of integration. But two limits is 4x. We doesn't know limits for y. Also, there exists an important step that's called limits. We should find the new limits. Depend on the new variable. At x equal 0, see, at x equal 0, that means that y also equal 0. At x equal pi squared also equal y squared, so y equal pi. Now we say that the new limits is from 0 to 2 pi. By substitution in left hand side, the integration will be definite integral from 0 to pi cosine y times dx. It will be 2y dy. Put 2 outside the integration, it's constant. Now definite integral from 0 to pi y cosine y dy. Y times cosine y, two functions. Also, two functions are main function, so we use integration by parts. Integration by parts to find I1. I1. Now by parts, we have u and du, dv and v. Let u equal 2y, so du equal 2 dy. And let dv equal cosine y dy. Now v equal sine y. We know the rule of the integration by parts. uv minus integration v du. Now I1 equal uv minus integration v du. But we have bounded integration. We have two limits. Two limits for all function. U times v, that's equal 2y sine y. 2y sine y from 0 to pi. Minus integration u v du. That's equal to outside. Integration for sine y dy by the same limits. Put y one time by pi, it's equal pi sine pi, and the other time by 0, it's equal 0. And also sine pi equal 0, so all these parts equal 0. Negative 2, integration for sine y is negative cosine y. Now, negative cosine, negative times negative equal positive. Cosine y from pi to 0, it's equal cosine pi minus cosine 0. Cosine pi equal negative 1. Cosine 0 equal 1 by the same sign negative. Negative 2 times 2 equal negative 4. That is the required of this example. Now we note that bounded integration from 0 to pi squared cosine root x dx equal negative 4. The following example shows that definite integral from 0 to pi over 2 for the function dx over 4 cosine squared x plus sine squared x equal pi over 4. We notice that the result is angle. So we can imagine that the value of this integration will give us the inverse of trigonometric function sine minus 1, tan minus 1, sec minus 1, that give us angle. Now we have for left hand side cosine squared plus sine squared, but not with the same coefficient. Cosine squared have 4 and sine squared have 1. Now we're thinking about the relation between sine squared and cosine squared. We can put sine squared and cosine squared in one function, which is called tan x. So we divide it by cosine squared in numerator and denominator. As you see, first divided by cosine squared and also divided by cosine squared. 1 over cosine squared, it's equal sec squared. We can cancel cosine squared, but sine squared over cosine squared equal tan squared. This is an important step for solving this example. Now we can write it in the form of squaring. 4 is 2 squared and tan squared is 10x all squared. Remember how we can find integration gives tan minus 1. Integration dx over x squared plus x squared. X squared is x all squared. The function inside the brackets, its derivative is 1. Also we have 1 beside dx. It's direct integration. That means that the basic condition for tan minus 1 or sine minus 1 or sec minus 1, that the function tan x has its derivative in the numerator. G by dx for tan x is sec squared. That's the form for tan inverse. That's the form of tan inverse. Now we have a equal 2 and x equal tan x in the rule. The result will be 1 over 2 tan inverse x over 2 tan x over 2, all by the limits from 0 to pi over 2. Now put x by over 2 and put x by 0. It gives us tan. Remember that tan pi over 2 equal infinity. And tan minus 1 for infinity gives us pi over 2. Tan 0 equal 0. Tan inverse 0 equal also 0. Again, tan inverse pi over 2 over 2, that gives infinity over 2, all infinity. Tan 0 equal 0, so tan inverse 0 also equal 0. We're searching for the angle which give us tan for this angle gives us infinity. It's also pi over 2 times half. It's equal pi over 4. Now we proved that definite integral from 0 to pi over 2 dx over 4 cosine squared plus sine squared equal pi over 4. Notice that trigonometric substitution we have 3 roots. 3 roots. If we find any of one of them, we can write down its substitution. If we have root a squared minus x squared, a squared minus x squared, we can write down x by a sine theta and dx equal a cosine theta d theta. And also, if we have root x squared minus a squared, we write down x by a sec theta and dx equal a sec theta tan theta d theta, its derivative. And also, root a squared plus x squared, we write down x by a tan theta and dx by a sec squared theta d theta. Remember that this substitution is basic substitution for. Now remember that we put x by a sine theta. That means that we can cancel square root. Let we see that. Let we have root a minus x. Notice that when we have x squared, we put sine, sec, tan, all with power 1. But if the root variable minus constant minus variable, but x of the first degree, so we put sine squared. If we have x squared, we put sine. If we have x, we put sine squared. That means that we can cancel square root. Let we see. And d by dx now will equal its sine x squared. We write down 2 and it's equal to sine theta. Also its function now is theta, and the derivative for the function inside the brackets is cosine theta d theta. Now put x by a sine squared and take a as a common factor and take it outside. It gives root a. 1 minus sine squared is cosine squared. We can cancel 2 by the square root. It gives cosine theta. Now we notice that we cancel squared root. That means that it's possible substitution, trigonometric substitution for this example. Now, for the following example, show that definite integral from 0 to 1 root x over 1 minus x gx equal pi over 2. Let we write left hand side as root x over root 1 minus x. Notice that we have root 1 minus x. We have x of the power 1, and all this form is form for sine. So we put x by sine squared as a equal 1. To find gx, 2 sine theta cosine theta. Now, to find limits, we say before, in definite integral, we must find step of limits in substitution method. Limits, let x equal 0, so sine square theta equal 0, then sine theta equal 0, and also theta equal 0. On the other hand, let x equal 1, so sine squared equal 1 and sine theta equal 1 by taking square root. We notice that theta will be pi over 2, so the new limits is from 0 to pi over 2. Left hand side, from 0 to 1 root x over root 1 minus x dx, it will equal from definite integral from 0 to pi over 2 root sine squared over square root 1 minus sine squared times 2 sine theta d theta cosine theta d theta. Now root sine squared is sine, 1 minus sine squared is cosine squared, taking square root cosine, cancel cosine by cosine and put 2 outside, so the integration will be from 0 to pi over 2 sine squared d theta. In chapter 2 we said that sine squared and cosine squared not directly find its integration. We should write it by a new form, by the double integral of cosine theta. So we write sine squared theta equal 1 over 2 1 minus cosine 2 theta. Now we can cancel 2 by 2. Integration for 1 is theta, and for cosine 2 theta it's equal sine 2 theta over the derivative of the function, it's 2, from 0 to pi over 2. For theta, from 0 to pi over 2, it's equal pi over 2 minus 0. And for sine, let we put 1 over 2 outside, and it's equal sine 2 theta, and theta equal pi over 2, that's equal sine pi, and put theta equal 0, it's equal sine 0, all this is 0. That means that all value of this integration is pi over 2. That is the required. We proved that integration from 0 to 1 for root x over 1 minus x dx equal pi over 2. Now, example. If definite integral from negative 1 to 1 e power negative x squared dx equal k, find the value of integration negative 1, definite integral from negative 1 to 0 e power negative x squared, the same function, x squared dx. Now we notice that the greatest area is from negative 1 and 1, but we should put point 0 between negative 1 and 1. We write down 0. So we have two parts, from negative 1 to 0 and from 0 to 1. By using the property of definite integral, that integration from negative 1 to 1, we can write it by negative 1 to 0 and plus 0 to 1 for the same function. But we have, if the function is odd, and we have negative a and a are equal but with the opposite sign. If the function is odd, that means that it's equal 0. That means that all of this area is equal 0. And if the function is even, we can write it down by 2 from 0 to a for the same function. Let the function equal e power negative x squared. To find the type of this function, put every x by negative x. That means that f of negative x equal e power negative for negative x squared. That's equal e power negative x squared equal the same function. That's the condition for even functions. That means that the function is even. Now the function from negative 1 to 1 e power negative x squared dx equal to definite integral from 0 to 1 e power negative x squared. That means that k equal k. That means that definite integral from 0 to 1 for e power negative x squared dx equal k over 2. K over 2. Now, this part equal k over 2 and total integration equal k. So the integration from negative 1 to 0 e power negative x squared dx equal also k over 2 from negative 1 to 0. From negative 1 to 0 equal k over 2. Example 2. If n is an integer, for any value k, satisfy the following integral. Definite integral from 1 to k for the function x power n minus 1 dx equal 1 over n. Find value of k. Find value of k. Left hand side is definite integral. To find this value, we have two steps. First, we should find directly the value of the integration. Second, we substitute by the upper limit and lower limit. Adding 1 to the power, that means that the result of integration will equal x power n over the new power n from 1 to k, also equal 1 over n, right hand side. We can write 1 over n outside. That means that 1 over n times x power n all from 1 to k equal 1 over n divided by y 1 over n for the two sides. That means that x power n from 1 to k equal 1. We can substitute by the upper limit, that is k. It's equal k power n minus, put x by 1 to the power n, it's equal 1. Put negative 1 in the other side, 1 plus 1 equal 2. So k power n equal 2. We can find k, that's equal 2 power 1 over n. That's the value of k. Satisfies that the definite integral from 1 to k for the function x power n minus 1 dx equal 1 over n. That's for all for definite integral. Good luck.